So, I'm going to be talking about how changing the size and shape of the glottis contributes to controlling phonation. So, before we get started, this is my paper larynx, and here you see we have the cricoid cartilage, thyroid, epiglottis, arytenoids behind here, and then these, I have to get really close, are my makeshift vocal folds. Oh my gosh, I hope you can see, and ventricular folds. So the vocal folds are located within the larynx at the top of the trachea. They are attached from behind the arytenoid cartilages to the front of the thyroid cartilage. I'm like moving this all over the place. The ventricular folds are commonly referred to as false vocal folds because they have been thought to not be directly involved in the production of our normal voice since they don't typically vibrate, but they are part of our articulation actually during glottal stops. Okay, so for the epiglottis, the position of the epiglottis can be changed through two main ways. The first is by contraction of the aryepiglottic muscle, which is just basically a band of muscular fibers of the arytenoid muscle that extend from the arytenoid cartilage to the side of the epiglottis. So the aryepiglottic muscle can lower the epiglottis or change its configuration by folding it inward upon itself from top to bottom and or across. The other mechanism that changes the epiglottis is the result of the elevation of the laryngeal housing. Oh, I dropped a vocal fold. This elevation forces the front of the epiglottis against the base of the tongue, pushing it back and down over the upper opening into the larynx. This helps protect our airway from keeping us from accidentally breathing in our food or liquid into the pulmonary apparatus during swallowing.
So this section is going to be about how change in mass affects laryngeal function. And so before I start, here's a little bit about the model to set up where we exactly are in the vocal tract. So here's the thyroid cartilage. On this side we have the cricoid cartilage, the two arytenoid cartilages. Then if you were able to look down in there, you'd see these rubber bands that represent the vocal folds and the ventricular folds, as well as the epiglottis that would cover the air path and the trachea when we eat. So since those bands are a little bit hard to see, I kind of like to think of the vocal folds, which is what I'll be talking about, between these rubber bands. So here's it at rest when it's stretched out, and then when they come together they get a little bit thicker. So basically how mass affects laryngeal function is that any object that is capable of vibrating is also capable of creating a tone, and so that is how the vocal folds produce our voice, through vibration. And this vibration determines the frequency, which is dictated by two factors: the mass of the object, so the mass of the vocal cords, and the tension created by them, so how stretched out they are. So as the mass is increased, so if this is our resting position, the mass is increased, they get closer together, the bands get slightly thicker, and thus the mass goes up and the pitch goes down. When the mass is decreased and they get stretched apart, the tension increases and so does the pitch. So there's less mass but higher pitch. And this is something that can be familiar to us in the idea that the thicker strings on a guitar have a lower pitch as opposed to the thinner strings, as well as the idea that men generally have more mass in their vocal cords and thus have a lower voice, like lower pitched. And yeah, so we can see that this affects our ability to, our laryngeal function, in that when we want to create a higher pitched sound, we will stretch out our vocal cords and have less mass, as opposed to when we want to make a lower sound, they will come back together and get more bunched up. It's hard to see on this white band, but it gets just slightly, ever so less dense, has less mass as opposed to more mass. So that kind of shows how the mass of our vocal cords affects laryngeal function, mainly affecting pitch and the way we speak.
Hey guys, today I'm going to be talking to you about the stiffness of your vocal folds. This is my larynx. Thank God I'm not going to art school because it's not very good. And because I don't have rubber bands, I'm using these cool little bracelets to represent my vocal folds. They're stretching. So the stiffness in your vocal folds are due to muscle contraction. So the more contracting your muscles are doing, the more stiffness your vocal folds are getting. So just to show you by example, it's like when you're taking a deep breath, all that muscles are contracting, your vocal folds are going to be like stretching out very big, very wide. And similarly to when you're speaking and your muscles aren't doing too much, but plenty, your vocal folds are just going to be like wobbling around there. And then when your muscles aren't doing any contracting, if you're just quiet and everything's stable, your vocal folds are just going to be normal. So the point is, the more contracting your muscles are doing, the more stiffness your vocal folds are. Thank you.
Okay, hi guys, so my name is Rabia and we're going to be talking about the laryngeal airway resistance. So the laryngeal airway resistance is pretty much the opposition by the larynx, which is this, to the movement of air through the laryngeal airway. So pretty much it's the resistance to airflow during inhalation and expiration. So because the main constriction within the larynx is at the level of vocal folds, which is the blue rubber band, you guys can see that it's colored in blue. So it's at the level of the vocal folds. This region of the larynx is the primary contributor to laryngeal airway resistance. So the ventricular folds, which are the yellow one, if you guys can see that it's colored in yellow, right here, this one. So that's going through right here. So the ventricular folds are a secondary contributor compared to the true vocal folds. So by adjusting the cross-sectional area and the length of the internal larynx in this region of the vocal folds and ventricular folds, the laryngeal area resistance will likely change. So resistance increases with increasing constriction and length of constriction. So it's important to know that laryngeal area resistance is airway dependent. So that means that even at fixed cross-sectional areas and or lengths of the laryngeal airway, the value of resistance is influenced by how fast air is moving. So laryngeal airway resistance is not measurable. It's calculated by the quotient of translaryngeal airway pressure to translaryngeal airflow. So the range of potential airway resistance values is pretty large and can go from a low resistance, which means wide open air, to infinity, which is pretty much airtight closure of the airway. So it's common to think of laryngeal airway resistance in terms of a value that represents the average opposition to airflow through the laryngeal valve. So this average opposition is often taken to reflect the magnitude of coupling between the trachea, which is below the larynx, so it would be, we don't have it drawn here, but it's below it, and pharynx, which is above the larynx.
My name is Kathleen Kalschmidt, and I'm going to be talking about opposing pressure of the larynx. So this is our paper larynx model that we made. As you can see, we have the thyroid, we have the epiglottis, we have the arytenoids here and here, and we have the cricoid in the back. So we used this rubber band to show the false vocal folds. I'm actually just going to take it out to show you where the true vocal folds would be. So in here we have it. It's a little bit difficult to see just because we had a little hard time with construction, but it still gets the job done. So these would be the true vocal folds. And this is going to be what's moving and what the most amount of pressure we deal with in with the larynx. And so now I'm gonna explain it. So what first starts out is there's subglottal pressure on the vocal folds from the lungs. The vocal folds are going to be about here. And this just happens with inspiration and expiration, which is just breathing. And that's called, what it's called to open the vocal folds, the amount of pressure is called phonation threshold pressure. Air moves transglottally, which means it's inferior to superior. So the air moves from the lungs up through your trachea to your vocal folds, and then the pressure pushes on the vocal folds and then goes out. So that happens with breathing. Once the vocal folds are open, pressure is decreasing and air velocity is increasing. That's the Bernoulli effect. That's an application of the Bernoulli effect that we can see working in the body. And decreasing pressure is then going to eventually bring the vocal folds back together, which is called abduction. And that's it. Thank you.